hide what?
Okay. All right. Sorry about the owl thing. Yeah, thanks for having me. It's a real pleasure to be here. This is not what I'm going to talk about. The reason I'm showing this is because I thought it was funny. So this is what's consumed my life for the last year. This is a proposal that Kyle Leach, who's in the audience, and Dave Moore and I put together. Which button is it? Down here, where we're proposing, and actually have started now, to optically tweeze nanobeads, which are full of radioisotopes, do SQL sort of level optical measurements of the recoils of the bead under, say, when something happens inside, and then build a pixel calorimeter to detect, say, beta electrons coming out of a beta decay for all kinds of particle physics reasons. Specifically, my life has been totally dominated by this awfully difficult problem of how do I make a pixel detector to catch beta electrons in the sort of like 100 to 1000 keV range, which I thought was going to be a trivial old school particle physics thing, but it turns out is really hard. I don't want to talk about it because I thought it was funny. I've never been in a room where I thought that quantum limited radioactive measurements were sort of overrepresented before. And not one for a crowd. And plus I told Shimon I would talk about something totally different. Let's see, how do I advance this? Okay, cool. So what I'm going to talk about is this kind of idea that probably you've seen various bits of this idea floating around in the past decade, that you can test quantum gravity in a let's say, a terrestrial experiment. So I've been working on this seriously since 2014. My training is actually in string theory, roughly speaking, and I left that to really pursue this aggressively. And it's a pleasure to actually be able to talk about experiments that are starting to happen and what they mean. I see. So the basic line of questioning, you have to get this clear right off the bat. Okay, we're asking a very simple question. We're not asking about ultraviolet physics. We're not asking about black hole physics directly. What we're asking is just, is the gravitational field a quantized degree of freedom in nature? So, more concretely, you can ask like things, can I put the gravitational field in the quantum superposition? And how would I know that I did it if in a real lab? It should be said that the answer to this is yes, under the strong priors of almost all theorists. Okay, so this is really just an experimentalist question in my view. You really want to make sure that your prior was not wrong. This is the cartoon of sort of a schematic of one of the ways you could try to do this. Okay, I imagine I have some source mass. This is something I can control in my lab. For example, this is a levitated bead in Marcus Asselmeyer's lab. That bead has some non-trivial amount of mass, and therefore it sources some gravitational field. So what you'd like to do is superpose the field. How do I do it? I just superpose the mass. The mass is now in two locations. The field is correspondingly superposed, with two different minima. Okay, suppose I did that. How do I know? How do you know a gravitational field exists in the first place? You let something drop and see where it goes. So schematically, you would have some test particle and let it gravitate onto the superposition and ask what happens. So under sort of standard assumptions, where the answer to this would be yes, which is what I'm drawing here, what you could see, for example, is that the test mass would become entangled with the source mass through this gravitational interaction. If this mass is here, it goes that way. If this mass is here, it goes that way. And then the superposition is an entangled state. So I thought I would do one of these sort of fun talks that everybody's doing. So I organize this as a FAQ. Okay, so this is all the questions I get when I go out into the world. So one, do we have a theory of quantum gravity that works? Okay, I'll try to give you a precise answer. The answer is yes, actually. A different question is, what if gravity isn't quantum? Okay, what the hell is the alternative to this theory? That's a hard question. Okay, then we'll get into more experimentally oriented questions. So can I detect gravitons like in a real experiment? And what's the implication if you can? And then related, but not in a direct way question is, can I detect entanglement generation by the Newton interaction like I just showed you, again, in practice? And if so, what would I learn? And then this is a little bit of a grab bag item, but since I just wrote a paper, I want to show the result. So maybe you've heard of this or maybe you haven't. There was a lot of press a couple years ago. Eric Verlinde and Catherine Zurich proposed that there would be very large quantum gravitational fluctuations that you could measure in an interferometer. It's actually kind of a revitalization of an old idea by Craig Hogan. And so I'll sort of tell you what, so I'll have some precise statements about that. Yeah, this is also organized so that like if you've had any of these questions, you can just pay attention to that and then tune out. There's going to be a lot of ideas you've probably never heard of in this talk. It's a little out there stuff, I understand. So no, not going to take it personal if you don't listen to all 5. Okay, so do we have a theory of quantum gravity that works? So I give a lot of talks in like sort of not high energy world. And I think this is an underappreciated fact that we do have a quantum theory of gravity. It works exceedingly well, actually. Here's how it works. You just take the Einstein action. So this is just the Einstein equations come from this action. You write the matter coupling term in the exact normal way. And then you just make the assumption that I'm in a region where space is roughly flat or roughly the field of the Earth or something like that. This is probably the owl. Now, how do I get the controls back? Oh, geez, I'm not going to worry about it. You make the approximation that I'm in some background field, and then I have little fluctuations around the background, so little fluctuations around flat spacetime, for example, and I just treat those fluctuations like a quantum field, just like you would treat the electromagnetic field in a QED. That works. It used to be believed that it didn't work because it's a not renormalizable model. Until the 70s, that was considered a fundamental issue. Starting around the 70s, we realized that actually most field theories are of that form. And what that means is they're effective quantum field theories. They just work within some range of energies. And this particular effective field theory works for energies where these higher order infinite series of terms, which are a series in the curvature scale in units of the Planck mass, are small. Okay, but the curvature in units of the Planck mass is small everywhere, unless you're near a black hole singularity or at the very early universe. So this theory actually works exceedingly well. These corrections are enormously small. It's also kind of the only thing you can get under standard assumptions of a quantum mechanics. So if you assume, this is old work by Steve Weinberg, if you assume that the universe has unitary time evolution and is a Lorentz invariant and satisfies a kind of weak notion of locality, this is the only, and is consistent with the Einstein's equations, this is the only thing you can get at low energies. In particular, for example, string theory reduces to this model in the energies in the lab. So I highlight this because what I'm going to be talking about can be viewed as a test of these properties in the gravitational sector. I think that's actually the clean way of thinking about it. Okay, that's our theory of quantum gravity. So what is the alternative to that? Now it gets ugly. Okay. Here's quantum gravity in a quantum information diagram. You think quantum gravity is difficult, has d-branes and stuff. No, it's just two massive objects in your lab. So 2 pieces of metal, 2 atoms, whatever. They interact with a Newton 2-body operator. Everything with a hat is an operator. So this is an entangling 2-body interaction. You can derive this from the graviton picture by just having virtual gravitons exchange. It's a simple calculation. So what else could happen? This is sort of the general class of things people have thought about. We don't know if this is the whole, like there's no classification of things that aren't this, but this is sort of everything that exists so far. So these are models where I have 2 things in my lab that I can observe, and then what happens is they don't interact through this 2-body operator, but they interact through some kind of 1-body operators where, say, the mass of one guy feels the average location of the other. So this is a nonlinear Schrodinger equation, right? There's a psi here, there's a psi here, and there's a psi here. It's nonlinear. This has been known for a long time to have basic problems if you take it too seriously. The way you get around those problems is by adding a noise. So this is like some classical stochastic noise. I'll show you a concrete example of how this really arises in the next slide. But this is a very general statement that in order to see some kind of semi-classical gravitational interaction, I have to be adding noise to the system. It's almost a definition that these non-quantum gravity models do not entangle objects. This is a 1-body operator, not a 2-body operator. And then, yeah, like I said, they necessarily come with noise. Maybe you saw in the press recently, Jonathan Oppenheim in London has a long series of papers proposing a sort of relativistic version of that, and that would fit into the classification I'm talking about. His model involves a path integral that takes 4 lines in a LaTeX file, so I don't want to show it. I want to show something simpler that you can get your head around. This is a concrete way of making a model of two things interacting through gravity in a sort of classical looking way. Jake Taylor was my boss at NIST, and we used to call this adversarial gravity. The way you picture this is you're living in a quantum simulation. The simulation has been designed to trick you into thinking that there's classical gravity. The way the simulation works is at every time step, so this is some Markov process, and I'm showing one time step. At every time step, something in the computer measures the location of your two masses. That's what this entangler and this measurement do. The computer now knows to some error, say sigma, where are the masses. Now it just generates with a feedback operator the gravitational field generated by this guy at this position on this other guy. So that'll create some, you can make any equation of motion you want out of this actually, but in particular, you can get equations of motion such that on average, the trajectories of particles will obey Newton's law, including the gravitational force. So this is supposed to explain why, for example, large things like planets orbit large things like stars. However, quantum mechanically, the model is different, and so you have to think, well, so then you can try to measure the difference at smaller scales. This model has two free parameters. So it has a parameter of how accurately are these position measurements being done. And it has another one that controls, you can either do large feedback interactions rarely or weak feedback interactions often. So that's a parameter V. Sigma is the error on the positions. Okay. And so what that means is it's some sort of almost particle physics-like thing you're doing where I have a parameter space and you can try to constrain it. Okay, so this is just a simple example of how you would constrain such a thing. That model, because it has noise, or alternatively, because it violates unitarity, has all kinds of nasty behaviors. For example, objects heat randomly. They just sit there and heat. So this is like a spontaneous collapse model, if you've seen those. The other thing is that the gravitational field itself is a noisy object, right? It doesn't measure the positions exactly, so it's not feeding forward exactly. And so there's some shot noise in the gravitational field just intrinsically. In that specific model, these have some parametric dependence. And so you can make a plot of like what's excluded. And, long story short, if you're, okay, this is just something Jake and I did. So probably there's more excluded by smarter people like Masha, but, roughly it seems that there is some chunk of parameter space for models like this that are not dead on arrival. And so what you're going to try to do in an experiment is either rule it out all at once, by testing if gravity can entangle things. If gravity can entangle things, this whole model's off. Or you can ask, like, does gravity generate anomalous noise, and then sort of parametrically start excluding things, like a particle physics experiment. That's sort of non-quantum gravity at the non-relativistic scale. I just want to flash, because I'll use this in a second. What would non-quantum gravity look like in the radiation field? So this is okay, so if gravity is quantized perturbatively, you have gravitons coupling to stress energy. So this is a model of, let's say I have a detector, gravitons talk to my detector by just coupling to its energy. What else could happen? Okay, the classical sort of toy model people use is I have my detector, it's quantum again, but now a couple of this is classical random external field, H mu nu. You can allow it to be classically random, just like in the previous slide. Again, I'm not showing the noise terms here, just for brevity. And I want to emphasize again that the only sort of serious proposal to try to put this into one of those non-relativistic pictures is this stuff by John Oppenheimer. I'm not going to talk specifically about their models, but I'm happy to take questions. Okay, so that's supposed to set the stage of sort of like this ideas that we're testing. Okay, so now I want to talk a little bit about how do you test it. So let me start with gravitons. Igor is going to talk a lot about this and give a slightly different take, but mostly the same take, I think. So you can ask, and Dyson famously asked, can I detect gravitons? And Dyson actually is a beautiful paper with a sort of mixed answer. I would say now, really the answer is yes, you can detect single gravitons. And this is a room full of people who know measurement theory. So this is really fundamentally just a statement that I can measure the gravitational field in the number basis, as opposed to the amplitude basis like LIGO does. So this is a really cool idea by Igor's group. This is a very concrete way of doing this. So this is a Weber bar. Okay, classically, a Weber bar, a gravitational wave comes through, it makes the metal vibrate. and then you measure the vibrations with some voltage readout or whatever. Okay. So you can make that fancy. You can make it quantum mechanical. Let's say this is in the ground state, and I can do single phonon readout. Now people can do this. Maybe not in a Weber bar of this size, but you can do this in many systems, of course. So quantum mechanically, then you'd say, okay, this big wave of gravity comes through. It's made up of, let's say it's made up of gravitons. The bar absorbs one of them. That gets converted into one phonon, and then I measure it. Cool. The really nice advantage of this system is that it works in the frequency regime where we already know we can see gravitational waves. So there's definitely a signal. There are other ways that aren't in that regime. So I think the original way is Dyson, actually in this classic paper, pointed out that gravitons gravitons passing through a magnetic field can convert into photons, just like the axion diagram Masha showed. And so there's plenty of sort of axion experiments that could see an equivalent version of this just in photons instead of phonons. Those all work at higher frequencies though, and we don't know what the gravitational wave signals, what the sources are. There's another thing that's more recent, and I'll talk a little bit more about this experiment. This is a thing at Caltech that's being built by Lee McCullough called GQuest, where it's sort of like LIGO, except instead of a homodyne measurement, it measures sideband photons. And you can trace that back in measurement theory, and it's sort of equivalent to this. Okay, so let's say the answer is yes, I can count gravitons. And to be clear, that just means I can imagine a gravitational source like a binary merger and a detector that will click when the wave comes through. So then what you want to ask is, does that test whether gravity is quantum mechanical? And so, that's a hairy question. Here's a precise version of that question. Can such a measurement distinguish this model where the gravitational field is quantized from this model where it's not? And everything I'm gonna say is in these papers. So to answer the question, there's a room full of quantum measurement folks, so probably you've heard this. Let's go back to the photoelectric effect. So the photoelectric effect you often hear proves that the photon exists. Okay, is that really right? The photoelectric effect, I have these, I have bound state electrons, I shine light. If the light is above a certain frequency, some of the electrons are unbound and become photoelectrons, and then I count these in some detector. I see discrete clicks, and of course you can associate that to absorption of single photons. On the other hand, you can actually predict the exact same signal with a classical electromagnetic wave coming. So you just take two models like the ones I was showing, just in electromagnetism. I either have quantized electrons and a quantized electromagnetic field, or I have quantized electrons and a classical electromagnetic field. I open Sakurai, I look up how to do perturbation theory, because I cannot remember, and I do these calculations in both models, and lo and behold, the answer is exactly the same. The differential rate for conduction band, for excitation of the conduction band is given by a detector efficiency. That's the fractional absorbed power multiplied, it should be the expectation value of the intensity operator of the light, multiplied by a step function that enforces the condition that the frequency is above the gap of the detector. So all of the sort of historic things that were viewed as evidence for the photon are actually baked into this calculation that has nothing to do with photons. This is not my innovation. This was understood by Glauber. Oh, cool, I get to cite Glauber in his own building. This was understood by Glauber, and there's a beautiful discussion in Mandel and Bolt. So, I think the point would be seeing clicks in some detector doesn't require quantization of the signal, and this is going to exactly hold in the gravitational case too. You can ask, what could I do that would distinguish those models? I won't belabor this in this audience, but I think it's well known that if you can imagine certain quantum states that will produce click statistics in a detector that cannot be explained by a classical radiation field. So the sort of formal version is take a mode of the field, electromagnetic or gravitational works the same way. Look at the coherent states, convince yourself that you can write any state of a mode as a diagonal thing in the coherent state basis with a p function sitting in front of it. P function is normalized, looks like a probability. Is it a probability? Well, if it is, then this is literally a classical, you can just map this to an ensemble of classical wave. However, there are quantum states where P can be negative, and in those states, you can actually show that there will not be a classical ensemble description of some observable. Great example, sub-Poisson statistics, right? So I have my detector sitting there, I'm counting clicks, I put them in time bins, and I ask, what's the difference between the variance in the rate of clicks versus the average rate of clicks? If the answer is 0, it's Poisson statistics. If the answer is above 0, it's super Poisson statistics. So for example, thermal light shining on a photodiode. Then the kind of cool thing is that in quantum mechanics, there are these states where P can be negative. This is an integral over a function multiplied by a positive thing, the square, right? So if P is negative, though, you can actually organize that this integral is negative, and you can find states which will produce click statistics which have less variance than the mean, so sub-Poisson clicks. And this is famously observed in optics in like the 80s. So can you do it in gravity? The answer is no, to the surprise of probably nobody. But I think it's worth saying why. So the reason is detector physics stuff. Okay, so detecting sub-Poisson statistics, you need a good efficiency detector. Okay? Right, so formally the difference that you're going to observe in the click rate in the mean is proportional to this detector efficiency. And in a gravitational detector, the efficiencies are really low. In this Weber bar, it's about 10 to the negative 20. That's a ballpark estimate, but I obviously don't need to make a very precise ballpark here to draw the conclusion that you are always going to see Poisson statistics in a detector like this. The reason it's small is just because the gravitational coupling to matter is small. So as far as I can tell, this is a pretty general conclusion. Okay, next. Can I detect entanglement generation by the Newton interaction? Okay, this is a different question, and this one is a little closer to my heart. So people maybe have seen this proposal or heard about it. So this is a paper by Sogato Bose and a bunch of people in 2017. So this is a very concrete, this is why I like this paper so much. Really, they put some numbers on paper. So the idea was I'm going to have two masses, and I want to see if they can be entangled by the gravitational interaction. Okay, so what are the masses? They want to use NV-center diamonds. Why? Because you can imagine that I can send these things through a Stern-Gerlach and split up the spatial wave function to two locations. So that's what's shown here. Then you can imagine doing that with two of these next to each other. So you have some state where these L and R label either the internal spin and it's tied to where the mass is in the Stern-Gerlach setting. So the joint initial state is a product state. It evolves into some entangled state. How entangled is it? It depends on the Newton potential strength. Okay. Concretely, if you put numbers, the parameters you need to specify are the distance between the two diamonds on average, that's D. So I put in a millimeter here. That's to ensure that you're not getting nasty van der Waals forces between the diamonds and stuff like that. You can imagine superposing them over, let's say, a micron distance. So that's the distance between these two lines. You can imagine a nanogram scale diamond. Okay, so it's pretty aggressive to imagine superposing a nanogram over a micron. Put it lightly, but let's suppose I could do that. The real killer of this is that you need to then let it sit there for a second and integrate the signal. And by sit there for a second, right, I'm trying to do a two-body gate. So I really need to not have errors while I'm doing that. And okay, all kinds of things cause errors in a system like this, right? So in particular, for example, imagine doing this on Earth in a drop tower. There's gas in the tower, even if you're in some very good vacuum. So numerically, if you imagine you're in an XHV chamber, like at 4 Kelvin, okay, so pretty good isolation. The rate of gas collisions is sort of in the megahertz range, and I got to keep this thing coherent for a second. So draw your own conclusions. So that's a very, I think, downer take. But the reason I put this is to just say, the concept is clean. It has technical problems. I don't know if this exact idea is going to work. I don't know. But there's definitely, this is a room full of really good experimentally minded people. definitely room for a better version of this, and I've gambled a lot of my career on somebody coming up with one. So I encourage you to think about some variant on this. The concept is just take two masses, get them entangled, and then read it out somehow. A less ambitious thing you could do is go back to the drawing board and say, okay, well, why am I doing this exactly? So what I'm trying to do is I'm trying to do an experiment that can distinguish this sort of typical quantum gravity model from some class of classical gravity models. And so I emphasized before, okay, these entanglement tests rule out all of these because these models by definition don't entangle. But they also have this property that they're noisy. And so you could actually maybe just try to test this property. So this is something I've been involved in. So let's ask a simpler question. Can I reverse the gravitational interaction, right? Is there noise or is it reversible? Or, I'll use the word coherent sort of loosely here. This now becomes a quantitative question. It's not qualitative, like does it entangle? It's how noisy is the field versus a technical noise in my lab. So this is a way to do that. This is maybe not the best way, or it's certainly not the only way, but this is a way that we, with Holger Mueller and Jake Taylor, we proposed actually 3 years ago now. And there's a bunch of follow-ups about the interpretation of this. I think we've all settled on what it is. The proposal, just as a concrete experiment, was take a source mass, let's say a high Q oscillator, high Q so that it's not itself noisy. And then I interrogate this thing's gravitational field, for example, with the thing in Holger's lab, which is a lattice atom interferometer. Okay, so this is my cartoon of a lattice interferometer where the atoms start in one well, and then I split them into two wells. I let this superposed atom state interrogate the gravitational field of this source mass, and then I try to recombine the atoms and see if they've lost any phase coherence. And the point of doing this, there's two advantages to this. So the basic idea, right, is that if gravity is quantized as per normal, then gravitational interaction itself will not cause any loss in phase coherence. In particular, if you make this an oscillator, if you start the atoms in some state, then after one period of the oscillator, the state of the atoms will have to return to itself, modulo technical noise. On the other hand, in these non-quantum models, gravity is not reversible. And so what that does is you're necessarily going to induce some loss of phase coherence here. And so, as an observable, you'd see something like, here's quantum gravity, and this red line is one of these noisy gravity models, and you're just trying to see if you can tell the difference. There's some actual rate for the loss of coherence you can work out in a model like that. It has the same free parameters v sigma. And this is some number like, well, okay. I mean, I'll show you some numbers in a second. Of course, what you really do is you say, okay, actually in my lab, I don't put this oscillator there. I measure all the technical noise. I have a coherence time for my atoms by themselves. Now I put the torsion balance in, and I compare the observed decay rate of the atoms to the decay rate without the torsion balance. And then I can make some quantitative constraint on this parameter by saying, I for sure know that if I don't see any extra decoherence from the mass, then I know that this isn't there at some level of precision, and that gives me a bound on sigma and V. So we're doing this, believe it or not. And by we, I mean Holger and Matt's in the audience, so Matt is actually really doing this. So this is the sort of concrete setup. So this is the lattice atom interferometer. Holger's has one in the lab. We're building a new one. So it's just, a laser field. I don't want to get into all the details with people in the room who know way more about this than me. But, in particular, you can trap the atoms and you can superpose them over sort of micron scale distances. And then the source mass is a high Q torsion balance being made by these guys at NIST who are really, really good at that stuff. This is being made at NIST. This is in Berkeley, being built in Berkeley. We'll integrate them ideally over the summer here. And start trying to do these measurements. And the sort of 5-year goal is pretty conservative. We're really just trying to rule out about 2 orders of magnitude on that parameter space I showed you. Okay, so two last comments, and we'll get to lunch on time. Okay, that's a lot of sort of how would you think about doing these various experiments? Okay, what the hell would you do these for? So I gave you a good model, which is quantum gravity, and a crazy model, which is this classical simulation model, just to make things concrete. What people I think would mostly want to know is, does the graviton exist? And so the connection of these experiments to the graviton is a little subtle. And I think the only sort of precise technical statement is, I'm going to show you my version, but there's an earlier version by Alessio Palanca and Bob Wald and Marcus and a bunch of people. The basic idea is the following. If I can entangle things through the Newton interaction, if that was all gravity could do, that would be inconsistent. That would generate various paradoxes like superluminal signaling. So to get rid of those effects, you have to add in quantized gravitational radiation. That's sort of how they phrase it here. There's a sort of more technical version of this in terms of scattering theory. Again, if I have a model where scattering is unitary and Lorentz invariant and has a 1/r entangling interaction, and you can actually just show that model also has to have quantized gravitational radiation in the asymptotic states. This is just a consequence of the optical theorem. Basically, for the particle people, if I have this diagram, I have to be able to cut it into having gravitons going out on the external states. So again, I mean, it's a quantitative statement in some of these models, but we're testing these assumptions, and so therefore you are sort of getting some information about whether the graviton exists indirectly. Okay, last thing, this is fast. Who's heard of this? Anybody? Okay, a couple people. Good. Yeah, the guy from Caltech. All right, so this idea was first put up by Craig Hogan and then has been revitalized, and it's been really fun to think about this over the years. So this is a diagram from my paper, but there are other diagrams by these people. Okay, whatever. The idea is the following. So this is phrased very conservatively. What I'm going to do is I'm going to build an interferometer. The interferometer starts with 1 mirror here and 1 mirror here. Okay. I'm going to shine light, and I'm going to measure the distance between the 2 mirrors, just like LIGO does. So you can ask, what's the variance in the observed length due to quantum fluctuations of the gravitational field? So if you just ask for the variance of this path length, the variance is technically defined as I shoot a photon here, I wait for it to bounce back and hit here, and then I read off a time on my watch, and I call that twice the distance. You're worried about relativity stuff. If you say that gravity is quantized, like I've been discussing, the sort of standard graviton physics, there's some answer for the variance of this length, and it goes like the Planck length squared. On the other hand, what these folks have suggested is that, well, okay, so fine, gravitons predict that. What if in full-blown quantum gravity, there are various weird things that we think might happen? You could imagine that the scaling is different, that the variance is proportional to the baseline, so the initial distance times the Planck length. So the baseline is huge compared to the Planck length. So this is an enormously larger signal. Why would you think this? Okay, so I can't read minds, but the sort of rough picture is the way you calculate in normal quantum field theory, things can fluctuate independently in all 3 directions in space. Holography is this idea that, and so many serious results on it that say that the amount of entropy in a region of space is not bounded by the volume, like you would think in a field theory, but bounded by the area. And so that kind of suggests that you can't have things fluctuating independently in all 3 directions. And it might even suggest that it fluctuates less. And so that's sort of what this is saying. As an experimental point, though, so it's kind of interesting if I actually plug in numbers. So if you put a LIGO-like number, like a kilometer, for the baseline, this thing is totally unobservable. Okay, this actually would become observable. In fact, if you put the overall coefficient of 1, this variance is 3 orders of magnitude above LIGO's noise floor. So this would be way ruled out. And the only way you can get rid of that conclusion is by saying, well, actually, okay, we don't know, maybe it's frequency dependent or something, and it's not in the LIGO band. The other thing I want to emphasize is a theory point, but the sort of core statement here is anything like this would be a huge violation of effective quantum field theory, which is interesting. It might happen. However, it's definitely would be strange, and in particular, would violate locality in a big way. So, okay, that seems pretty academic, except that people build experiments for this. So there's this one. This is called the holometer. This was at Fermilab. Maybe you heard about this. This was actually, it's a really cool device. So this is LIGO, but scaled down to be the size of this person. And I think we're looking at it from above. This is not in space. It's actually in a shed in Batavia. It measures, gravitational strain at sort of megahertz band. So, or a couple orders of magnitude above the LIGO band. Otherwise, it's basically LIGO. It's a homodyne interferometer, et cetera, et cetera. This is a schematic of the new thing that they're building in Caltech called GQuest. This is a really cool system. I really am excited to see this thing come online. It's basically LIGO again, scaled down again, still looking at megahertz. But what they're going to do is, instead of homodyne readout, they're actually going to strip off the light, filter it like hell, measure sideband photons. So the idea would be the gravitational wave comes through, drives a sideband photon, and then you detect that with an SNS PD, which is sitting in a cryo chamber off to the side here. It's pretty sick. Okay, and even as just a sort of, you're looking for gravitational waves, it's cool because the noise properties are better. It's a the Q&D readout and all that stuff. But it's been certainly partially driven by the idea that you're going to look for a signal like this. Great. So last slide. I swear to God. So here's sort of my editorial comments. So this whole graphic noise idea could be true. We really don't know that much about ultraviolet quantum gravity. But you should know there is no detailed model that predicts this effect. And in particular, string theory, and therefore ADI-CFT, which is a result in string theory. String theory reduces to graviton physics at low energies, at least perturbatively. This is the statement that there's a spin-2 massless string mode. So these models do not predict this effect, at least in perturbation theory. Maybe there's a non-perturbative effect, and that's sort of, I think, the open question here that I definitely don't know the answer to. In particular, though, the graviton calculation, and we actually worked this out finally and published it. The graviton calculation is finite. There's no ultraviolet divergence. There's no infrared divergence. So there's no reason to think it's going to break down so far. Maybe you should go to the next loop order or something, but naively, this calculation works. And in fact, this is the detailed prediction once you include the detector and all this stuff. So we really worked out did the input-output theory. This is the prediction for the noise power spectrum of gravitational signal. The dark line is LIGO. The dotted line is GQuest. They're different because they're different baselines. So this turnover is at the free spectral range of the cavities. And just for comparison, so there's a strain noise in normal units compared to LIGO. So LIGO is at 10 to the negative 23, so it's 10 orders of magnitude above this plot. Right, so this is not observable. Again, the surprise of nobody. This is just the Planck length, basically. That said, we really don't know what's going on in ultraviolet quantum gravity, and so it's still worth looking for this. All right, back. Okay, do we have a theory of quantum gravity? Yes. Please come out with that if you didn't have it before. What if gravity is not quantum? It's going to be something weird. Once you start violating quantum mechanics, it's nasty. There's no unitarity. Who knows? Okay, it's big. It's a nice theory question. Can you make a better model? A really elegant model that would say, well, actually, maybe gravity isn't quantized. Maybe it's this cool, nice thing. Can you detect gravitons? Yep. But as far as I can tell, they don't distinguish between quantum and classical gravity. And like I said, Igor will give, I think, a slightly different take on that later. Like Masha said, you shouldn't listen to any individual theorist too strongly. 4, can we detect gravitational generation of entanglement? I think eventually. I don't think we're going to do it tomorrow. If you do, it does distinguish in a very clean way between classical and quantum gravity. Great. What do you think about the Hogan-Verlinde thing? Big if true, pun fully intended. But yeah, it's a huge violation of basic graviton physics. So again, if you see it amazing, your priors should probably be kind of, well, okay, you can choose your own priors. My priors are a bit low. All right, I'm done. Thanks.
You mentioned testing Schrodinger-Newton theory with experiments and can exclude some parameter space. Is there a lower bound of the parameters you can limit, then you eliminate the theory completely?
Yeah. Thank you for this question. So actually, yeah, the answer is, okay. So I don't know, we don't have a classification of all such models, but in the specific one I showed, one reason I like to show that model is because there is a lower bound. So actually, let me go even further back so I can show you why there's a lower bound. So there's two free parameters. So this is the parameter space of the sigma, which is the accuracy that the computer is measuring positions versus the sort of feedback timescale. Okay, so there's an anomalous just decoherence of stuff or anomalous heating that has some scaling with V over sigma. There's a shot noise in the gravitational field, which goes like 1 over V. And so put together, what that means is you can attack this from above and below. And I mean, I didn't draw it, but this triangle closes. So there's a finite region here. And so you can go up and you can go down. And in fact, an experiment like the one I showed does both because you bound this effect and this effect. So it's not a bottomless search. Giorgio, oh, sorry.
So this may be it's actually off topic, but
Great.
it's sort of inspired as following comment. So first of all, when you show the fact that the bar detector is very inefficient, reminds me of why we have neutrino oscillations that are clearly quantum mechanical phenomena, and yet none of us is able to get quantum money in the neutrino physics. And the reason, it's actually fundamental reason, is that the quantum efficiency to detect neutrino expressed in quantum terms, the language of quantum measurements, the quantum efficiency is 0. And so you cannot do an EPR experiment. Okay, the quantum mechanical effect is there, but it's essentially useless from the point of view that one cares about. Now, but there is another thing that I on the other hand, find very confusing. That is that both very weak interactions we see, gravity and weak neutrino interactions, so they're both kind of really difficult things to do. Neutrinos, for some reason, we detect quantum, and we haven't been able to detect wave nature of those things, and which would presumably dominant in radial neutrinos, in big bang neutrinos, but no one knows how to deal with those. And gravitational waves, kind of equal or even more weak, we see waves, but as you point out, it's really hard to see in quantum.
Yeah.
I don't think this is completely sort of random words, but I find this sort of maybe there is some deep connection or interesting thing one can say about this, but I don't know what it is. Okay.
Okay, can I try two things?
Huh?
I don't know if these are interesting things, but let me say two things. So one is the wave, to detect directly the wave nature of neutrinos. People have imagined, for example, the Studolsky effect, right? So you have the coherent background, it generates a torque on a polarized material, and that would be very much like a coherent amplitude detector style of those things. Not that anyone's done that. I would say you've kind of detected the wave nature in the sense that so in neutrinos, okay, there's many reasons to know that they're quantum. One in particular is that you really see an interference effect, right? When you see the oscillations, it's interference. And so the question is, can you do a gravitational analog of that? That's how I kind of actually view these experiments.
Yeah. Great talk. This is the question I asked of total ignorance, but like when you were sort of saying, okay, if you accept unitary scattering and these other things, you mentioned it said also that you need like a Newtonian scaling of gravity, like you had like kind of the standard, 1 over r.
Yeah.
And like, how do like searches for short range gravity, which I think we'll hear about from Giorgio, like modifications to gravity, fit with all of this stuff? Does it just like violate, or does it mean you could have a classical theory of gravity where you have short range scaling that's different, or
Yeah, really nice question. So, okay, when you actually try to prove this in detail, what you find is, so you could do this with the Yukawa interaction,
Yeah.
okay? The kind of input here was like, okay, suppose, sorry. So you can put a Yukawa and try to run the same argument. So suppose I find that gravity actually does have some, Yukawa-like modification. Then this actually still works. And this is why I say it is quantized gravitational radiation. Okay, so this phrase carefully is chosen to mean I have a coupling proportional to G Newton in the masses, and it radiates, but it can have a mass. There's nothing in the theorem that would say that wouldn't. In fact, if you see the Yukawa-like form of the potential, it implies that you would have to have radiated particles at the mass given by the Yukawa length. Yeah.
So in quantum optics, you can get noise. That noise comes from a quantum field in its ground state. People talk about exotic gravity that causes heating. If this is classical, should I think of that? Where does the energy come from? Is there some giant reservoir of energy floating out there that I could tap into somehow?
Yeah.
That's causing things to heat up?
Yeah. I think that's like the most weird thing about all these models. So again, we don't have a classification of all these models, but in all the ones that exist, that is the answer. There is just a reservoir of energies doing something. So they're pretty weird.
Okay.
And so then it becomes a quantitative question of how well constrained is the presence of such a thing. It's a good question. Again, there's not a detailed enough model to really say much. In the one model that has been put forward, this thing by John Oppenheim, it actually does. And then actually that causes a lot of weird pathologies in the prediction. So it's a game to see if you can make such a thing that's not ruled out already. Yeah.
Okay, so we restart at 1:30 after our lunch break. Let's thank all our speakers again.